Welcome to this explainer. Today, we're taking a high-tech factory tour to uncover exactly how NVIDIA's revolutionary RTX Spark superchip is actually manufactured. We're going right down to the microscopic level to see how the physical hardware that's literally reinventing the PC gets built from the ground up.
So, let's just dive right into this fascinating question. For years, running massive generative AI models and ultra-heavy compute tasks meant you needed giant, power-hungry servers sitting in some remote data center. But the RTX Spark, it changes all of that. We're going to explore how that massive data center power was physically shrunk down to fit right inside consumer laptops and desktop workstations.
Here is our incredibly quick factory tour map for today. 1. The blueprint. 2. The silicon. 3. Advanced packaging. 4. The inner die connection. 5. Memory and power. And finally, number 6, the final superchip. All right, section 1, the blueprint. The monolithic chip is dead. To really understand this marvel, we first have to look at why the traditional approach to making computer chips just had to be completely abandoned for this project. Instead of relying on one massive, error-prone block of silicon, what the industry calls a monolithic die, NVIDIA shifted to a highly efficient chiplet architecture. You see, trying to build one giant chip means a single microscopic manufacturing defect ruins the entire thing. So by breaking the processor into specialized, smaller pieces, they physically separate the general computation from the intense graphics execution. And this massively improves manufacturing yields and drives down costs.
Now, what's super interesting here is that the RTX Spark is partitioned into two distinct physical components, both manufactured at TSMC. On one side, we have the S die, or the system die. This contains a custom CPU laid out by MediaTek, which, by the way, also handles the memory controller. And then on the other side is the G die, or graphics die. This is fully designed by NVIDIA, using their Blackwell GB20B architecture, and it handles all the heavy tensor and graphics pipelines.
Moving on to section 2, the silicon. Fabricating the 3-nanometer dies. Okay, so down at the microscopic level, now that we have our blueprint partitioned into two dies, both the S die and the G die are fabricated using TSMC's absolute cutting-edge 3-nanometer class process, specifically their N3E FinFET node. At this impossibly small scale, the transistors operate at much lower gate threshold voltages, which drastically reduces active switching power and sub-threshold leakage. What does it actually mean for you and me? Well, it means they can pack literally billions of logic gates into an incredibly power-efficient, tiny footprint that is absolutely not going to melt through your laptop case. And looking closely at the customized MediaTek CPU sitting on that 3-nanometer S die, we see a 20-core ARM v9.2 processor, and it's split perfectly down the middle. You're getting 10 Cortex X925 performance cores to handle those high-frequency, intense operations, and 10 Cortex A725 efficiency cores optimized for low-latency background processing. It is honestly a masterclass in balancing sustained PC power with mobile energy efficiency. Which brings us to section 3, the glue, advanced CoWoS-R packaging. Right, so now that we have our CPU and GPU dies beautifully fabricated, we hit a massive engineering hurdle. How do we physically glue these separate pieces of silicon together so they act as a single cohesive brain? NVIDIA solves this puzzle using an advanced 2.5D packaging technology called CoWoS-R. That stands for chip-on-wafer on substrate with a redistribution layer. Instead of using those highly expensive, rigid silicon interposers you typically find in massive data center servers, they utilize an organic interposer mounted on an organic package substrate. Think of it like a microscopic, highly cost-effective superhighway connecting the two silicon cities. Structurally, this all happens step by step. First up, you fabricate the S die and G die. Then, you mount these dies side by side onto that organic interposer using incredibly dense physical microbumps. Finally, you bond that entire interposer directly to the package substrate. It literally takes separate logic blocks and physically merges them into one consumer-friendly, thermally efficient package. Section 4, the connection, the coherent CPU-GPU link. Now, just putting the chips next to each other on a substrate, that isn't enough. They need to talk to each other flawlessly and instantly. This is exactly where NVIDIA's proprietary NVLink C2C, or chip-to-chip interconnect, comes into play. It utilizes all those tiny physical microbumps in the packaging we just talked about to route communication directly between the S die and the G die. It completely eliminates the traditional hardware boundaries that usually bottleneck your CPU and GPU on a standard motherboard. And the sheer speed of this interconnect is absolutely staggering. We are talking about roughly 600 gigabytes per second of bidirectional bandwidth. Let's put that into perspective for a second.
That is roughly 5 times faster than a standard high-end PCIe Gen 5 configuration. Data is just flying between the CPU and GPU almost instantaneously.
Because the physical latency across this NVLink connection is so incredibly low, it creates something really magical, a unified, coherent address space. This means both the MediaTek ARM CPU and the NVIDIA Blackwell GPU can read and write to the exact same physical memory addresses. There are 0 software-level copy penalties slowing things down. And guys, this right here is the secret sauce for drastically speeding up massive AI calculations.
Next up, Section 5, Memory and Power. Feeding the beast.
So, we have our perfectly connected superchip. But a chip this powerful cannot function in a vacuum, right? It needs massive amounts of data and electricity. Check out this number. Soldered directly to the motherboard, wrapping closely around the processor package, are 8 high-speed LPDDR5X memory modules. This gives the RTX Spark up to an incredible 128 gigabytes of unified memory. And because the CPU and GPU share this massive pool, the system can load massive 200 billion parameter AI models completely locally.
But how do you manage all that juice? Well, MediaTek integrated a brilliant power management IC, or PMIC, directly into the package. It dynamically scales electricity on the fly. Say you're just browsing the web, it sips power in the single-digit wattage range, giving you that great all-day battery life. But the second you fire up local AI training or real-time 3D rendering, it instantly ramps up to 80 watts for laptops, or even up to an incredible 140 watts in the desktop DGX Spark workstations. Which brings us to our final section, number 6, the final superchip, desktop to data center.
Zooming out from those microscopic components and the power delivery, what can this beautifully manufactured hardware actually achieve once it's fully assembled and powered on? Well, the result is literally a desktop supercomputer. We are talking about 1 petaflop of FP4 AI performance and 6,144 Blackwell CUDA cores. It can render 12K video, run massive AI agents natively right on Windows without even touching the cloud, or if you're an enterprise developer, it scales. You can literally link DGX Spark nodes together using ConnectX-7 networking to run gargantuan 405 billion parameter models. NVIDIA's CEO, Jensen Huang, really captured the essence of this whole hardware shift perfectly. He notes that by physically bringing the full AI data center stack down to a single consumer superchip, the PC fundamentally changes. It moves from being just a tool where you click and type to becoming an active, intelligent teammate that actually does the work for you.
Seeing how the RTX Spark is physically built, from the 3nm chiplets to that organic CoWoS-R packaging and the blazing fast NVLink, it completely changes how we view our computers. And it leaves us with a pretty fascinating question to ponder. If this level of microscopic engineering and raw supercomputing power is sitting right on our desks today, what incredible architectures await us tomorrow? Thank you so much for joining me on this factory tour, and keep learning.